All right. Well, I hope y'all had a great weekend. Had a great Mother's Day at that. It was Mother's Day yesterday. So I know things were pretty busy around here. We're in the process of building our next chicken coop. It's a brooder coop. Um, I'm just giving an introduction here. Jumping on a few minutes early compared to usual and just giving everybody time to kind of jump in. So thought I'd tell you about my brooder coop we're working on. So, yeah, it'll be somewhere we're actually trying to experiment with doing a little chicken breeding. We just hatched this week, last week, technically last week, I guess. We just hatched our first round of chicks that we raised here or had here, laid here. Whichever comes first. So yeah, that's exciting stuff for us. How are y'all doing? Are you having a good time? Is busy season treating you well? I know we'll dive into the questions here, and we've got a really good one asking about cooling tower economizers. I do have a I have one question um, from the portal for this inside of Chiller Academy. So if you don't know, if you want to get say priority questions or whatnot, feel free to go to chilleracademy.com. There's a free portal for this, for the Chiller Questions Answered series that you can get signed up into. And from there, you can post your questions ahead of time. You can see the previous streams, and it's far more just organized and structured and easy to follow. And, more interactive. I'm far more engaged at that point. Um, Instead of just kind of waiting for the stream here. So that's up to you, right? We will have time. I've only got one question there in queue, and then we'll jump into the comments. And then I've had some really good questions coming in terms of the I guess call it the backlog. I've been saving a lot of these questions that for a long time, like I would answer them or I'd try to engage with them as best I could, that through just comments and stuff or maybe emails I get. But I'm actually intentionally saving these now into a database for this stream so that we can jump in and I can actually take some time to talk through these things deeper. Because one of the things I've realized that I never really considered before was everybody's got these questions. These are almost always questions that multiple other people have, and these are questions that there literally may not be anywhere else to get an answer, right? So one of my things I want to do is, okay, well then let's provide that answer, and then let's give that answer in the context of a chiller technician. A lot of resources online that I come across, they're not in technician context, they're in some other context, which then if you're already struggling to understand the concept to begin with, well, that's just going to have you even more lost because they're looking at it from a different angle than we would as a technician. And it's not always directly comparable. How you doing, guys? I'm just letting everybody kind of jump on here. I see we got Tom in the chat. We have Jason Johnson here today. Hey, y'all, go check out Jason's channel, by the way. People ask me for field content and stuff anymore. Jason's your man for that, and I would encourage others to get engaged in that too. If you've been toying with the idea, um, just take a few videos and post them out there and just see what happens. You never know. We need good people sharing this information so that we can give more examples, and it makes it easier for those who are interested in getting in this side of the field to see what life is like doing what we do. We are the elite of our industry. There are for the scales of what we do, what we work on, that's something I want to really push out there a lot more. We are genuinely like the top end elite of what our industry offers. And so like that can be a lot of weight, it can be a lot of pressure, very daunting to consider as a person, but I also find it encouraging, and personally I find it inspiring that just what it is that we're doing, the level of genuine infrastructural support that we bring to our nations. um, it's incredible. Like, it's just mind blown. Anyways, please explain purge unit, troubleshoot. Yeah, okay. And the control wiring. That differs a bit depending on the chiller. Is there a CVHF chiller with 514 gas? Have abrupt bearing failure. I've not heard of that. Sorry, I'm just kind of rolling through some of the questions, kind of seeing what we got in the queue. Oil pump, refrigerant pump, working principle. Oh, yeah. Okay. Yeah, those are tied together via a gear. There's an internal gear. Cool. All right, well, let's get into our first question. Now, this question is going to, it's actually much longer than this. This comes out of the portal on the Academy. But I will read the full question, and I'll have kind of a snippet here on the screen. I have a Trane CVHF refrigerant cool VFD open loop system. My cooling tower is a Tower Tech. I'm having issues with the high pressure compressor surge. My first diagnostics. I found my cooling tower circulation pumps VFD on bypass, not auto, which I then put on auto. But while I was performing a diagnostics, I put on hand and ramped them up because I'm getting a lot of air in the system. Okay, so you put the pumps back in hand and you force you force the flow up. That's an interesting. Okay. I also ran the system for about 20 minutes, and I found my saturation temperature at 70 degrees and my pressure differential was at 7 degrees, which at the time should have been at -3, right? So as of right now, I got my, he says purse, I think he means purge unit, running consistently for the last 72 hours, added a Ref Tech purging system with a filter dryer and moisture indicator on my vapor inlet and a filter dryer on my liquid outlet. Going to my liquid line, got to go back for a startup. Any recommendations? Or do you think there's anything I missed? There is a lot of air in this system. Thank you. Yeah, I would first, if we're gonna pose a technical question, this is a great way. It gives me a lot to work with and go off of and try to explain and express in this process. So I do appreciate the level of care and detail put into it. It's kind of hard to fit all that onto the screen here, but that's fine. I can figure that part out on my own. So you've got a CVHF. You're having trouble with it, dealing with high pressure and surge. The pumps were in hand, it sounds like. You put them in auto, and so let's pause there first as a first step. I would be cautious defaulting to putting drives in auto if I don't already know what's driving the auto piece of it. So one of the things to keep in mind is the automation system may be struggling, and you may not have a system that needs a variable loop. And so what I mean by variable flow, you may not have a variable flow setup. So at that point, unless you just know that plant should be running in auto and there's a properly tuned control loop in the automation system that is monitoring where that speed needs to be for the pump for flow and GPM and such, I wouldn't recommend just automatically just putting it in auto without further having any other context. Now, maybe you have that context. I just don't. It wasn't obvious to me in the way you broke that down that we did. But so I would be cautious of that, first of all. Yeah, very cautious of that. Now, ramping that back up makes sense because then we're increasing our GPM and our differential across the heat exchanger, and so having a high having a surging and high pressure issues, that makes a lot of sense that we're going to get that. Now I'm assuming you walked into this plant probably already having surging problems from the sounds of the conditions. That is true. So I get the thought process of, okay, well, why don't we go ahead and put the pumps. I would, if what I would rather see is that my pressure differential, even if the pumps are in hand, fine, leave them in hand. I'd rather see that my DP across the condenser is within range, right? And if you don't know, uh, pretty for those, especially if it's a smaller tonnage, somewhere in the 3 to 5 6 psid has been kind of just a baseline for your smaller, less than 1,000 ton machines. And then as they scale, that's going to change a bit. But yeah, that would be one of my first points. I care way more about what is my DP in that circumstance than what speed is my pump being allowed to run at, and does it need to be a variable speed or not. Honestly, if I'm dealing with a surge condition in the first place like that, I would much rather keep the pump in hand so that it is consistent, because I don't want the pump trying to vary and modulate to be another factor that I'm having to calculate into my troubleshooting. It just becomes far more complicated at that point. Okay, so that's my thoughts on the pump. I do want to, if you don't know, for those who may not know about what's being referenced in the 70 degrees versus the 7 degrees on the pressure differential. So on these Tranes, there is an actual liquid line sensor that's where we're pulling our saturation refrigerant temp from. So that sensor is right down in here, right? So this is your liquid line drop leg. This is the first phase of the flash. So you've got a flash plate in here. So we go into a medium pressure, but right in this little section here, this is where you've got a liquid line sensor. That sensor is where these machines are pulling their refrigerant saturation temperature from. Now, for a lot of your modern machines, you will actually have a condenser pressure transducer. Some of your older ones didn't, but this was something that the newer ones do. So you can take these. If your machine doesn't have a transducer, then you would end up connecting a pressure gauge to the top of the condenser, pulling your condenser pressure, and then you're going to compare that to this saturation temperature and see where they're at. Now, he's indicating that those are there's a 7 degrees of saturation difference, which is a indicator that we do have a lot of atmosphere in the chiller, which that atmosphere is going to cause significant head pressures to rise, surging problems, like a lot of the symptoms that he's currently describing. That's where those symptoms are going to be coming from. So that's what's being referenced there in terms of saturation, and the pressure differential was at 7 degrees. So that would just scale out on a saturation scale, which is, yeah, like way too much. That's so going the route of, okay, we need to get a purge system online. So in terms of recommendations, that would be one of my next steps. Is I do want to verify, one, is the onboard purge working correctly? Is the temperature sensor on the suction line for that Trane system, being the Earthwise purge, is that suction line on the purge unit actually reading correctly? Because that'll have a huge impact on whether or not we're pumping out correctly. So did we verify that sensor? Have we verified that the purge filter is actually working as well? So that's going to help draw the moisture specifically out of it. But what I've actually seen those, if they don't get changed routinely, maybe yours has, but if they don't, I've seen it to where they can actually start to plug up, and you'll start running really high liquid levels inside of uh, your non-condensables evaporator chamber. Like your liquid levels will start rising. There's a little sight glass there. You'll see that those levels start getting high in there. That could be a symptom of that filter dryer getting stopped up. So is that clear? Are the valves clear? So what I mean by valves is there's an isolation valve on the liquid drain valve, and there's an isolation valve on the hot gas intake valve for the purge system. Are those actually open? Are they working? That'd be another thing I'd want to confirm. So like just an overall, is the purge system working? And I would end up going through a troubleshoot process until I felt confident that it was. Now, I'm really glad that you put one of the RefTech portable purges on it. Those are actually fantastic. And you also put the dryers on it as well. That was another good move. So those RefTech, the dryers specifically are going to help with the moisture aspect of it more than anything. So if you are having a lot of moisture latent issues for some reason, which if you're drawing in a lot of atmosphere, that will happen. You will start to accumulate moisture in the system. That's why these dryers need to be there. If your focus, so this is just my opinion, if your focus is getting the non-condensables out and less about there being a moisture issue, which are somewhat different, then I probably would worry less about the dryers, because those will slow down the non-condensable removal process, because now we're trying to process through those additional dryers. Again, if we're worried about moisture, the dryers make a lot of sense. If we're more worried about the non-condensables and getting those out of the system, then I would be more worried about just letting that purge just rip through those non-condensables and getting them out of there. But having the RefTech the RefTech portable purge is a really good next step there, as you did. Now keep in mind that if you're keeping the chiller online and allowing it to run, which you mentioned that you let it run for about 20 minutes. So keep this in mind, that the onboard purge is only the most effective when the chiller is actually online and running, because they're pulling at a midpoint on the condenser. So if we come back over here, you can actually see the purge vapor line. You can see the isolation valves here, right? So they're pulling off of a midpoint on the condenser. They're not pulling off of the top. So with the chiller off, those non-condensables are going to be stacking in the top, not down here at the midpoint. The reason they're at the midpoint is with the machine online and running, the non-condensables, due to the discharge gas getting pushed down and hitting this distribution rail and getting forced, they're going to be heavily concentrating right here as the refrigerant's getting pushed through the system and getting processed. They're not going to spend as much time stacking in the top. But with the chiller off, the non-condensables are going to rise, and they're going to spend a lot more time hanging out at the top of the condenser barrel. So I would want, or that's where the portable purge really comes into play, is you can hook it up, connect it to our service ports on the top of the barrel, and then allow it to really process that down without having to risk the chiller itself any further. So that's where that portable comes in. So that was a really good step in that direction. But once you get to a certain point, until you can run the chiller, you're not going to get a whole lot of effective use out of the onboard purge. So just keep that in mind if you're not already aware of that these are really designed to maximize during operation, and once you get past a certain severity point, they don't do a whole lot during the off cycle, but just because of where these gases are stacking into the system. So let's see. Okay, so got the purge unit running. We identified that we've got a lot of atmosphere. Got my liquid line. Yeah, so at that point, especially because you have the portable purge on there, I do expect that you're probably going to be like with enough run time on there, you're probably going to be okay, at least for a startup. Now, the other side of this is okay, so you've done all of this. Why is that atmosphere in there to begin with? That's one of my next big questions is okay, we know it's there. Why is it there? We really need to figure that out too, because this could be an annual maintenance thing. Keep that in mind. You don't specify what region you're in or what your climate conditions are like. Maybe this is a fresh seasonal startup, which at that point, I wouldn't say this is, it's not a good thing, but it's not necessarily abnormal. What's important though is if you have a machine like that and you are doing a seasonal startup for the warm season, then you really want to plan to do that pre-purge ahead of time, and specifically using that portable purge system to do that, not waiting until the chiller tries to turn on and destroy itself. Now that's up to the customer, right? We don't actually have control over something to that detail. They've got to decide to allow us to come in and do that routine seasonal thing. So yeah, just putting that out there. If this was a seasonal, I'd give it a little more leniency. Okay. If this is not a seasonal and this chiller has been online consistent enough in recent months, but now it's got all this atmosphere, why is that atmosphere there? So at that point, that's where you get into, I would recommend doing a pressurization. So get a pressurizer, hook it up, pressurize that chiller, and leak search the heck out of that thing. Figure out what is caused, and it could be something simple, right? There's been some of these cases where the the oil filter canister wasn't spun on just right, and it was causing a leak there. Or there could be just a simple a gasket or bolt somewhere, or the maintenance was recently done and the purge dryer didn't get reinstalled just right, and the little O-rings in there, maybe one of them got pinched. I've had that before. Machine stacks up, you start doing some leak searching, you find it, it's an easy fix. Just throw a new O-ring or address whatever it is. Doesn't always, especially if this was sudden, like this machine's done really well, nothing crazy has happened recently, and now all of a sudden we're having um, these major issues with atmosphere getting into the system. Well, then I would want to go to, okay, well, that sounds like potentially a maintenance related issue. Maybe one of the valves that was used to take an oil sample during maintenance didn't close or seat all the way. Maybe the cap got forgotten to put back on and that valve is leaking. Now it was able to sit for a period of time and draw a bunch of atmosphere in, right? There's a lot of valid reasons. That doesn't mean the worst case scenario, but we need to verify that. So yeah, once you get to where you can start up, that's great. Like it's good to get the machine running. I really care about why this was necessary in the first place. That that part's not okay. But that's my overall thoughts with your situation predicament and what I'm interested in addressing while I'm there. Is it a purge unit problem for the chiller itself? We have what kind of leak are we dealing with in the first place? Stuff like that. And I care more about the DP than what the VFD speed is on my pump. So, yes. All right. Yeah, and check regeneration solenoid on the purge unit. Yeah. Mm-hmm. Absolutely. Yeah, those solenoids on those Trane purges are just god awful. I was actually one of the Trane techs local, or I guess ex Trane tech now, was telling me that part of their annuals, or at least one of the packages they offer, is they'll literally go through on the annual and change out those solenoids, the valves on the annual inspections. as just part of the service because they are such a routine problem for those machines. Yeah. All right. Welcome, everybody. Hope y'all are having a wonderful day. Hope you had a wonderful weekend. I'm going to grab our first comment question here from Mr. Tom Froggy Man himself. If I sound like a nerd, it's because I am. All right. Ooh, actually, I do have. I'm going to pull up a picture for this before I get rolling. This is my thing, you know. Once I get rolling on my spill, I really can't disrupt myself too much. Otherwise, I'll lose my train of thought so severely that I just turn into. So I gotta set myself up for success, you know. I do have a picture of a plant with an economizer. Let me find it here. Where are you? Did I put it maybe here? Nope. Well, shiz. Maybe here. Okay, well, that picture's not where I thought it was, so I'm not gonna kill a bunch of time trying to find it. That's unfortunate. It was a good one too. Man, I really wish. Where are you? I really want to find this picture. It would do a lot to help with my breakdown. Okay, I'm not going to keep wasting time. All right, we will just go with what we got. Can we talk about cooling tower economizers? When is it efficient to use it? Economizer in combination with other chillers. So a cooling tower economizer is basically we're using the tower as our cooling source for the building, not just the condenser water for the chiller, but as for the building itself. To accomplish this, we need really low wet bulb conditions. And I'm not even going to say necessarily ambient conditions, because in some regions you can actually achieve really low, wet bulbs, even though we may have a decent dry bulb temperature. So essentially what we end up doing is we're going to process the condenser water through this heat exchanger. And what we'll have is a plated heat exchanger inside of the central plant. And that heat exchanger will process the chill water loop and the condenser water loop through it. Now, under normal mechanical cooling, so we're going through the chillers, we wouldn't utilize this heat exchanger. It would have bypasses installed usually that will completely divert around it and won't even process through it. In those situations, we don't want it to. But when we go into economizer mode, well, then we will actually divert to bypass the chiller typically, and then the condenser water will flow through one side of the heat exchanger and the chill water loop through the other side. And quite literally what we end up doing is once the plant switches modes, the condenser water set point will be lowered to around, say, 40-45 degrees. And we need to be able to hit those lower end metrics with the tower given our wet bulb temperatures. We have to take in tower approach, things like that, in order to achieve that. And quite literally, our cooling tower becomes the cooling source for the building at that point. So we're using the condenser water through the cooling tower to chill our chill water loop. Now, in some cases, when the plant will transition into economize mode, many times the plants I've worked in will also raise the chill water set point a bit. So instead of running a 44, 45 degree set point, they may increase to a 48 or 50 degree, and it just depends on the building and what its humidity load is like, which in these cases typically our humidity is down, right? So in the fact that we have a low enough wet bulb in the first place, we typically have a much lower humidity to begin with in this situation. And so running a higher condenser or running a higher chill water temperature is not that big a deal because we're not worried as much about dehumidification. It's just about processing some general level of sensible load. That's really our only focus. So at that point, we completely remove the mechanical load from the electrical system to cool that entire chill water loop. And where the cooling tower, if it's big enough to handle it, will be able to sufficiently keep that chill water loop processed on its own. And that is the whole concept, is the cooling tower then cools the condenser water down cold enough to then, through a plated heat exchanger, chill the chill water loop. And the chill water loop will still function the same. It's just going through the heat exchanger, the plated heat exchanger, which we call the economizer, instead of going through the chiller itself. And that is the main separation there. And again, there's going to be bypass valves that divert flow and do this appropriately so that we don't, when we're in mechanical cooling, we don't want to use the economizer, and vice versa with the other way around. And this will be something that some plants will have an automatic changeover where there's set parameters, and it's maybe doing some kind of load calculation on the building and the air handlers or whatever the load is at the time, and what the outdoor humidity and wet bulb temperatures are. And then once we cross this threshold for 30 minutes, X amount of time, whatever it is, it will go into an automatic economize mode, and everything will adjust and tune itself accordingly. There's a lot of plants that they'll do this manually, to where they'll monitor it. When they get into, say, the cooler season where it's more shoulder weather, they can manually go in and toggle something in the automation system, and everything will kick over into a economize mode. And it is significantly more efficient because at that point we're still running the cooling tower and the fan. And again, this only works if the wet bulb temperature is low enough. So if it's not low enough, there's no point, because we can only cool via evaporation in the tower as cold as our wet bulb temperature is. So at that point, we're strictly we have the load of the cooling tower fan and the pumps to cool the space without having to run whatever the load is through the chillers at the time. And at that point, while chillers have gotten a lot better about running at much lower part load conditions, they still tend to struggle. A YK be an easy example to throw under the bus, where if flow is not just right and you're not keeping the condenser water low enough, you get into those part load conditions that YK is going to surge, or going to struggle with surging far more. Where in this case, you kick that over to the economizer instead and just shut that YK completely off. Well, now all of that struggle that a YK may have at part load conditions just gets pushed off onto the cooling tower, which typically isn't that big a deal. So that's where it is more efficient. We just use far less energy in total, and that's how it can be used in conjunction with a chiller system. Now, before I move on, I do want to point out these systems do get implemented beyond just chiller context. There's some, if you're familiar with self-contains, there are self-contains on the market that have economizer coils that are in front of the evaporator coil. So when you're actually looking through the filter deck the coil you're seeing is your economizer, and your evaporator coils behind that. So those types of systems can also have will also use a economizing mode, where if the same conditions, wet bulb gets low enough, conditions are just right, instead of trying to run the self-contained system with usually scroll compressors at really low part load conditions and kill a bunch of energy with compressors throughout the building trying to stage at that, instead we can just cool that condenser water down, route it through the economizer, tell the compressors and the cooling inside of the self-contains to just turn off entirely, and then we can process the building load just through that what was condenser water for the self-contained is now functioning as economizer water, flowing through that economizer coil. But again, when we're not in economize mode, we're going to isolate that coil and only flow through the self-contained water-cooled condensers at that point. So this gets applied outside of chillers, and that's just another way this same type of technology can be applied. It's not a water-cooled chiller system. Now, one of the things that we really have to be careful with when we're doing this setup is we are intentionally inverting our loop. And this should play a factor in deciding whether or not to go into economize, because this depends on the chiller we have. There are some chillers, or a lot of chillers, who do not overcome an inverted loop on their own very well at all, if at all. There again, there are other chillers who can overcome an inverted loop quite easily. So getting into loop inversion territory is the danger of using a water side economizer, because if at some point we have to transition from economize on the plant level, okay, from economize to mechanical again, mechanical cooling, meaning we're turning the compressors back on, then we've really got to be able to overcome that, because one or two things can happen. If we can't get that condenser water temperature back up and get out of an inversion quick enough, we could either cause a severe migration with the oil into the evaporator, because that's part of what will happen. We'll just very quickly and rapidly migrate that oil over, and then we'll start tripping out on oil pressure, oil alarms, oil loss, things like that. So that'll be one of the symptoms of having a hard time making that inversion transition. Another one would be, and this was something turbo cores give me all kinds of fits on. With the turbo core, they need the pressure differential for cooling, because their standard package is they do not come with a liquid cooling pump to pump the liquid refrigerant from the condenser through the compressor. So if you don't have that and you're relying on the pressure differentials, well, when you're inverted, you can't feed enough refrigerant into that compressor to keep it cooled, and it will end up overheating on the inverter temperature because of it. So like, you can eventually overcome that, but it's kind of a pain, and you have to go in and do a bunch of manual overrides, especially with the time delays that you should run on those turbo cores. There's a lot of scenarios where they won't properly overcome an inversion, in my opinion. Now, one of the ways to get around that is just, you can install even if it's aftermarket, a liquid pump on the cooling line. So in that circumstance, if you are dealing with a system that has a economizer and you do get inverted, when the compressor goes to engage, we can engage that liquid pump, and we can physically pump the liquid refrigerant up into the compressor even if we're inverted, so that we can keep the compressor cool and we're not relying on a set differential, which I find it was about 5 to 10 degrees minimum on the entering waters difference, until I hit about 5 or 10 degrees above let me rephrase this. until my entering condenser water was 5 to 10 degrees higher than my entering chill water, I was struggling getting enough flow through the compressor for the cooling side to prevent a overtemp on the inverter. So a liquid pump can overcome that on its own because it will just force that liquid to flow through there without having to rely on differential pressure, which is what it does in its natural state. So take the inversion piece of it into account. If you're not expecting that, or you've got chillers that can just take that on the fly and it's no big deal, then you've got a lot more flexibility. But if you've got a situation where you know that you're only going to be in part load part of the day and you're going to need to stage on the mechanical later in that day, well, you probably don't want to go into economize in that situation. Especially if the team on site monitoring those chillers are not trained on what to do if the chiller has a hard time overcoming an inversion. Which, just to clarify, an inversion is your condenser water temperature is equal to, or in many cases colder than, your chill water temperature. So especially the colder than part, meaning they're backwards in terms of which one is hotter than the other. So having to overcome that becomes a major issue. And inversion goes far beyond just having cold condenser water. You could also have hot chill water too. But either way, that's the big caveat you got to be careful with. And it's not, it can't be just a willy-nilly back and forth process, because that's actually, that you'll lose a lot of efficiency there, and it takes a lot for a chiller to correct that inversion. Like, it's not that simple of a process. And how you can manipulate your bypass valves, and again, there's ways of doing it better than other ways, so it depends. But I'm a fan of it personally. When it's used correctly, when it's applied correctly, is an amazing tool to have in a plant. Amazing tool. All right. Good morning, everybody. Going into so the purge unit. I've done a few videos recently on the purge unit troubleshooting. If you want to go check those out, Javadine, really trying to pronounce that correctly, I'm sorry. I can go into it again today, but it is something that I've covered quite a few times recently, and so I don't want to hit the same questions too heavy too often. So I would suggest maybe go check out one of those recent purge videos, and I've done some recent purge troubleshooting videos, not only sitting like this explaining it, but I have some where I break it down in front of a purge as well, if you want to see that. So I've got it both ways if that's what you're looking for. I would suggest that in the moment. Is there a new CVHF chiller with 514A gas have abrupt bearing failure? Not that I'm aware of. Yeah, I don't know of the CVHs with 514 having major bearing failures. Granted, they've been shipping for some time now. I haven't seen one with 514 in the wild myself. But I haven't heard anything about them having major bearing problems. Now, here's something I will throw in there is every time one of the manufacturers tries something different, they end up having a lot of these weird failures, and there's this whole kind of generational cycle process that goes um, uh, through the iteration process. So they make a lot of mistakes. Okay. And I've seen this nearly every time we've had a major change, which changing the refrigerant and its properties is a major change in and of itself. And I've switching from say R11 to R123. There were many failures, particularly around leaks with systems like that, which you have excessive atmosphere, you get a lot of leaks, you're struggling with that, you will end up tearing the compressor up because of surging and things of that nature. So, like, it's possible that with this new refrigerant, there could be some weird underlying issues that come up. That's just Trane's got to work through and then put out service procedures and kits and whatever they need to address that. So, yeah, if yours was a retrofitted machine, that becomes even more likely. That's where I've really seen it the most, is when people start doing the retrofits. The retrofits aren't a problem. It's not a bad thing. But especially when we haven't learned all the lessons yet, and if it's a chiller that was one of the earlier ones done before they learned a lot of lessons, your risk may be far higher. All right, CVH oil pump and refrigerant pump working principle. Okay. Let's grab that. Paste. And I do have some examples. So let me pull those up. Just bear with me. I'd like to be able to show you. Yep, there's one. Heater, the motor. Okay. And then let's grab another. Oops. Just bear with me. Should have another. I'm looking for. So I've got a graphic of a gear pump. This would be a good place to show it. Because that's what all these are using. You know, they're all using a gear pump to compress. Oh, not that one. And to compress the liquid specifically, because liquid tends to not compress as well as, say, a vapor. Well, the second one I'm looking for I cannot find, so I may just have to go without it. Okay, yeah, we'll just go without it. It'll be all right. We can use this as an inside view. All right, CVH oil pump and refrigerant pump working principle. So these machines are using an internal pump assembly in the sump, and they both run through the same. You can see this assembly sitting off over here. So what we've got is the refrigerant pump comes in right here. So this is where the refrigerant line feeds in, and this is a liquid line coming off of the oh shoot, bottom of the economizer, bottom of the condenser. Should be coming off the liquid line here. So this pipe comes off the bottom of the liquid line, goes through this liquid pump, and this pump then sends that up into the motor and is injected into the stator assembly to help regulate the temperature inside the stator. And then it is able to drain its way back into the condenser. But you've also got the oil pump inside of here, which then comes through this block here. The adductor assembly is off to the side. The oil vent and drains are back over here on the back of the tank. And then the outlet side comes through this filter block assembly. It's also where your pressure regulator is. And then that outputs out and up into the bearing assembly. So all of that gets handled inside of this. And right here is the pecker head for your motor. And there's one single motor that drives these. This is just a single speed setup, which is where we use a pressure regulator to control our pressure, unlike say a YK that's using a variable speed oil pump assembly. Well, these are a little different. These are constant speed, and we're using a pressure regulator to control that pressure. And this is what you'll see on the inside. This is your motor. This is the actual stator. They've got the rotor pulled out here. You can see the bearings, and then you've got the pumps. So these are your connection points you'll see on the outside. This is where the pass-throughs are. These two here, or at least, let me see. Two of these are the sight glass, so it should be these two are sight glass. And these others are going to be your actual ports for like the oil ports and such. And then this will be your heater. So this is the base of the tank heater, keeping everything warm inside of there. So both pumps run off of that motor, and they're both connected to that motor shaft, and that is what makes them spin and operate to where we can pump the oil and it flows through the oil regulator. And then we have the refrigerant pump that is drawing liquid refrigerant in and then pumping that up into the compressor. And part of just, especially on, like they say, the refrigerant side, this is an actual pump assembly that even when we get into these inversions and low load conditions, we're not relying on just differential pressure to create this flow, but we're actually mechanically forcing that flow. And these are gear style pumps. So there's a set of gears that interlock in there, and we're using those gears to compress that. And I say compress, it's not compression. I should be cautious with my phrasing here. To pump. We're using these to pump the liquid oil or liquid refrigerant where they need to go, so that that's how we can distribute it. Whereas we're not actually creating a compression though. We're generating flow. That is the key point there with how those are set up, is they generate flow through them via a gear style assembly to push the refrigerant, to push the oil through. And we can do that without tearing it up, because of the gears are not, again, they're not compressing the liquid, but they are allowing a flow to be created. And we're and how the gears are able to push is a better way to say that, able to push that liquid refrigerant or oil out into these circuits the way that they need to. So that is your basic principles of how these are functioning and working. And we're drawing in the liquid refrigerant to keep the motor stator cool, and then we're obviously using the oil to inject directly into the bearings to keep those lubricated. We have what they call we have a journal bearing on the front side of it. It's like a big aluminum sleeve that we inject oil into. And then we've on the back side, our axial bearing or thrust bearing is a set of ball bearings that we're using on the back side of the compressor motor. All right. Hold on. You would like the side centrifugals that send condenser water from one chiller to the evap of another. The second chiller is used to heat the water for the building. Yeah, and I saw your video on that where you were kind of walking us through that plant, Jason. It is a cool setup. They call them the Templifiers. Yeah, and it's, it's really, that's just another one of those just really interesting kind of offshoot things we can get into, and we get to see an experience where we're literally using the chiller for it's a type of heat recovery, right? So some chillers actually have a heat recovery uh, module installed, and I think I've got one of those where I can quickly pull that. Let me see if I can show you one with a heat recovery. Yeah, right here. So we have a heat recovery condenser right here installed to where the condenser gas gets sent into the heat recovery cylinder or the barrel, and we still have the regular cooling process happening, but we also have this heat recovery heat exchanger as well, and this is being used to capture basically the superheat. So the superheat coming off of the compressor can be captured here, get processed into a heat recovery heating loop that can be used throughout the building for whatever it needs to be. And then the regular cooling tower, like, it's not doing all the cooling. This isn't replacing the condenser, but it's just working alongside the condenser so that we can then, the condenser isn't having to necessarily de-superheat as much as at that point. It does take some workload off of it. Don't get me wrong. It's not that it's not helping the condenser. It's just not replacing the condenser. But this would be one way where it's all one package. And I would venture to, I mean, I don't, in terms of which one is more efficient, I think it has more to do with what kind of heat capacity are you trying to achieve. So in this particular case, I'd say you're going to have a fairly mild heat capacity, being that this is just basically taking the superheat off the heat exchanger. But in in your particular case, you're actually sending that condenser water through another chiller, which is able to then significantly process a lot more BTUs out of that, and really, I'm not going to say it's replacing your cooling tower, but it can do a lot to substantially reduce that cooling tower load so that we can then repurpose that heat as heat somewhere else. And you could see this used in a variety of ways. There could be, beyond just comfort heating, you could see this in manufacturing facilities where they've got one process that requires cooling a CNC machinery to keep it from overheating, but they have another process where they need to do a bake chamber where they've got to put components in to heat treat them, or something to that effect. Maybe they're trying to dry paint, and so instead of having an electric heater assembly that's trying to blow into that room or that space to keep it, or to get it to the right conditions to dry the paint or whatever it is, cure the device they're creating, that they just got done CNCing over here. So they CNC it, they then pass it over here to this machine to then say powder coat it, then they pass it over to this chamber to cook it in the oven. Now I'm oversimplifying this, okay, but this would be a way that we can literally take the heat we're generating in our manufacturing process and then using it a second time to help finish our process somewhere further down the line, or somewhere further up the line. It's just so many ways that we can use those BTUs beyond just take them from here and then throw them into the atmosphere and then have to generate heat somewhere else. We can genuinely just repurpose them and do it very, very effectively, which that plant you showed in your video is doing exactly that. Really, really cool setup. I need advice on low oil pressure and Trane CVHF chiller after changing oil. He changed oil, repairing purge unit. Chiller tripped on low oil differential pressure. We have changed two filter and finally changed the oil regulator, but still not improving. Oil pump discharge is 7. Well, I did actually have a very interesting one very recently about this exact thing. So maybe this will be something to consider. Do I have that picture? Can I get that picture pulled up really quick? Let me show you this picture. I need to transfer it real fast. Let me pull this up though. Okay. Share. I can send it to my drive. Yeah, this was. I think this will help. Just be another option of what can happen, because we are dealing with real life. Here, almost got it. Right there. Okay, let's download this. I had it on my phone. I needed to get it on the computer so I could then load it up in the program here. So instead of this, come here, go downloads. Oop, where is it? Is it unsupported? Where'd it go? I wonder if it's a high. Oh, come on. All right, I can fix this. Hang on. I'm sorry. I'd like to show you this. I'm gonna take a second and I'm gonna figure this out. Just 1 second. I really want to show you this. Okay. Now let's go pictures, screenshots. There we go. Okay. Let me pull the question in. Okay. Now we're ready. Thank you for your patience. I need advice on low pressure on I need advice on low oil pressure on Trane CVHF chiller after changing oil and repairing purge unit. Chiller tripped on low oil differential pressure. We have changed 2 filters and changed the oil regulator, but still not it is still not improving. Oil pump discharge at 7p. So you've taken a lot of the right steps, right? Those oil regulators do fail. Sometimes you have to exercise them a bit, but you've got a brand new one put in there. You've changed that. Still struggling. I would verify the transducers, okay? Even though this may have been working just fine prior to doing the oil change, it's just weird stuff happens, okay? So I would want to verify that my tank transducer is reading accurately and that my oil pressure transducer is reading accurately, meaning the discharge oil pressure off the pump, because that's where your differential is being calculated from, is the difference between there. So I'd want to verify those. If I'm comfortable that those transducers are for sure good, then you're kind of in a bad spot. You have a good you have a good regulator. You've got a good filter. The filter's not clogged up. Hopefully, no. Here's something else to consider. Make sure your oil temperature is good. Okay, so that would be something else to verify. Let that oil temp come up. You said you had to change the oil. You've got fresh oil in there. Get that oil heater online. Make sure that oil comes up to operating temperature, which should be, what is that? A minimum of, was that 95? I've got it in my troubleshooting guide. 95, 98, something like that as a minimum. But for startup, it's actually going to go up until I think it was 120 before it allows 110 or 120 from off to on. But while you're online, it can drop into I think the upper 90s before it trips on low oil temperature, something along those lines. Either way, you need to make sure that oil temperature is up. That will influence the pressures because those pressures change or can change and be affected by the viscosity of the oil, which viscosity, the thickness, will change as the temperature is fluctuated. Okay, so that's one of the reasons why we need to get the oil up to operating temperature just for regular operation to begin with, is so that we have the right viscosity going through our bearings. Anyway, temperature would be 1. Now, the other thing that was, maybe it's a gasket internally. So just this last week, I'd been working with a team and they were really struggling with this. They had done the exact same. They changed the filter, they had changed the pressure regulator, they had done all the stuff. This is the backside of that filter block. This is that port for that oil. It is completely bypassing right here. Their gasket inside of there just tore. What caused it? Why it would have done this? Who knows, right? Life happens. It just, I don't know. We don't know why it happened, but it did. They fixed this gasket. Technically, if I understood them right, they just flipped it over because you can see that like it's a pretty symmetrical gasket. So they just flipped it, stuck it back on, everything worked. But they fixed the gasket, and that was actually their main issue. Now, here's the thing to keep in mind. It's far easier to do the other two and far cheaper, because to get to this point, that means having to completely recover and take that whole machine down. Now they've got to go through an evacuation process and a pressure test and a charge. Like, they've got a week's worth of work for this one gasket, versus you can change a filter really easy. You can change this, especially if you pressurize the chiller, which not everybody does. Some do hot swap, but you can change out this pressure regulator far easier, far cheaper than going through the expense and trouble of taking that whole machine down. And you've already got fresh oil in there. And if you verify your transducers, like you've done all the external pieces, well, that gasket could be an example of one of the few things left that there's no way to see that from the outside, like whatsoever. So if you know your pump is good, you've got amperage through the pump, all that stuff is happening. You're getting oil into the filter. You know that pressure is being generated to some degree, because something similar has happened for these guys. It's not that they had absolutely no pressure, but obviously it wasn't generating near enough. Like, it was very similar, like almost verbatim what you've described here. That was very much what we were dealing with there. So that was the process. We start here. Next step, filter. Next step, regulator, transducers. All that's good. We know we got the correct oil in there. We're up to temperature on the oil. All those variables are good. Then there's, other than just opening the system up, there's not a whole lot else we can do. So that would be my suggestion there. If you're comfortable and you're confident in the rest, it might be time to pull that filter block assembly and check it out. I've also seen it where those blocks have the ports internally can get plugged up. So the fact that you did an oil change, maybe you did that oil change because the system was in very poor condition and it really, the oil was just bad off, right? Maybe it had a lot of trash in it, junk, who knows what. Well, that stuff can plug up those ports. Now, it's not, I wouldn't say it's really that common, but it can happen. So I've seen it to where literally just changing out the filter regulator block became the solution. So just, yeah, that would be my direction there. You're in a tough spot. Like, it's a hard thing to suggest, and hopefully maybe taking that picture, snap a shot of it and show like, hey, talking with these other guys, this could be, something you can show the customer, this is a possibility, right? They face something very similar. This may be it, right? Because that's a hard thing to sell the customer is, well, we've done all this other stuff and it's still not working, but now we want to open your machine up and it's going to cost crazy amounts more, right? That's a pretty tough sell to get a customer to buy into when you can't guarantee what you're going to find when you get in there. Know what I mean? Especially when maybe it was working fine before you did the oil change. Maybe you did the oil change because you weren't generating pressure. Okay, so I mean, just, yeah, I don't envy you. I'm sorry. You're in a tough spot, but hopefully that kind of gives you some kind of direction to go with. It's supposed to get to hundreds. Oh, yeah. Yeah, I mean, it's this time of year. It's going to start heating up like crazy. I have a WSC Daikin centrifugal keeps losing oil on shutdown. Could this be the IGV leaking internally? It keeps losing oil on shutdown. Possibly on that, Stephen. Possibly. I'm trying to think through on that IGV assembly and how it's set up, and would that cause keeps losing oil? I think, Stephen, I'd like to know more. Okay, I see Jason jumped in on that too. Yeah, check the vent lines. Yeah, make sure it's all draining correctly. Supposed to vent refrigerant to the inlet of the IGV. If it's not operating correctly, then you can keep pressure on the sump and not allow the oil to return from the gear case. Yes, thank you, Jason. Yeah, I would want to know a little bit deeper on maybe having a little more detail on what's exactly happening at the shutdown and maybe what the conditions are. But Jason, what Jason is recommending there, I do agree with in terms of making sure that that the vent and everything is able to drain properly. That's going to be a key part of that. Thrust pump check valve. I replaced the TXV on a centrifugal. Now I'm facing difficulties fine tuning new TXV. Please explain easy way to fine tune TXV. TXV on a centrifugal chiller, 300 ton pilot valve. From 10 degrees off, I would monitor superheat, make sure all adjustments and final settings, close set point. Steady state operations. But it'd take at least half hour to reflect the adjustments we made. How long should I wait after doing some adjustments? I'm trying to think through how to answer that on the stream here. How do I want to go about that? Tejas, I'm sorry if that's not how you say that. If you would, reach out to me via email. I would like to discuss this a little further. And I'd love to see some pictures of your setup before I start making too many recommendations. So if you can take some shots of that, email it to me, and kind of let me see what exactly you have, that will help me get in a better direction there. So you can just send that to hvactime@hvactimetx.com. That'll go a long way in helping me help you. Because again, my mind goes several places or directions to go with that, and if I suggest the wrong thing, you could end up tearing more up than actually helping, and I don't want to do that. Can oil migrate? The oil can migrate. The oil can migrate. Okay. When charging up a chiller with a flooded evap, some guys are adamant that you need to first charge gas only. Gets up to 32, then charge liquid phase in order to avoid risk of freezing evap. What's your take on that? Yeah, okay. Yeah. Sterling, you're always stirring stuff, dude. Always, you've got the questions that are like, I'm just picking on you, but you've got the questions that tend to be so controversial. It's because you're in a controversial spot. That's what your problem is. You're being dealt with controversy, and so you've got no choice but to create something. No, I actually like this conversation, so let's I do have some thoughts on this, and let's break this down, because it is important to understand this part and whys. And I do explain a bit of this in the service training program inside of Chiller Academy. And part of my notes and stuff that I have in there, I actually kind of break this down. And it really comes down to just your choice, what you're comfortable with. So let's talk about it. When charging up a chiller with a flooded evap, some guys are adamant that you need to first charge in gas only until the freon temp gets to 32 degrees of saturation, and only then charge in liquid phase in order to avoid any risk of freezing the evaporator. What's your take on that, yay or nay? I think that it is a excellent practice and it is worth following, especially if you are not familiar with doing these types of charges. And I even say this applies to flowing water, right? Flowing water during a recovery or charging phase, and charging vapor first and then charging your liquid. These are things to help minimize any risk of freezing, because I mean, the risk, the consequences, all right? So we do have to weigh that. The consequences of something going wrong are ridiculously high. Like ridiculously high. Now, this gets back to sometimes when we gain experience and we begin to reach a more senior level in our industry, we will start to not go by the book as much, because we've learned enough, we understand enough. We will take shortcuts, and in many ways that's what they really are. They're shortcuts. They're a way to get to the same result faster, but we have enough experience and confidence to do that without breaking something. So in the early stages of this, by the book in your situation is flow water, charge vapor first, get above freezing saturation, and then charge liquid, and never stop flowing water. Now, when we start moving beyond that into these shortcuts, which is where seniors, you can get yourself in trouble, don't get me wrong, but this is where you can gain some efficiency. One, you don't have to, especially if you're flowing water and you've verified flow, like you know that you've got proper GPM, you can just send the liquid, because the water flowing water, moving water does not freeze. At least not to the degree that we're doing, right? I mean, it doesn't freeze. Flowing water will stay fluid. Now, it's not that you can't create ice crystals in there, but realistically, that's not going to end up causing a major problem. So yeah, at that point, the goal there is just to take a shortcut. The shortcut is we're going to skip the vapor part because I have water flow. Now, you could also flip that the other way around. Instead of having water flow, if you charge vapor first, and you get above that 32 degrees of saturation, technically you don't need water flow, because what will freeze the tubes is the liquid refrigerant below freezing temperatures, not the vapor. And this is also where push-pull is super effective. Push-pull, we are getting the liquid out of the chiller without dropping our saturation temperature. So we're not pushing that liquid into a freezing state while it is making contact with the tubes. So at that point, the water flow is redundant. Or even some people won't even flow water. They will strictly drain the tubes and clear them out, make sure they've got as much water out of them as they can. They don't even want to have water in the tubes because they're so cautious about it. Again, they've got their reasons why. If that's their standard, and that is a by the book way to go about it. But if you're doing push pull, if you're doing it correctly, you won't freeze the tubes, because once you get all the liquid out of the machine and you're just doing a vapor pull, that vapor is not going to freeze anything. That's not what causes the tubes to freeze. It's the liquid refrigerant left in the heat exchanger. And if that gets below freezing, that will freeze a tube. So depending on which way you go about this, there are shortcuts. And those shortcuts are what is getting argued about, on whether or not those should even be taken in the first place. And that really comes down to your comfort and experience in doing that procedure. And if there is any hesitation whatsoever, follow the book. One of the big things about by the book answers is that they will typically keep you out of trouble, even though they will be possibly harder and take longer. And the whole point of what makes a senior is being able to know when to apply by the book to be the most efficient and effective, and when you can work around it. Does that make sense? So I am in favor. Do I do that? Depends. Depends on my circumstances. Yeah, that's my summary. Hasn't filled me yet. Always try to run the pump as well. Yeah. Heating bundle. Thought as soon as I got flow, and there was no need. But if experienced guys like yourself do it, then I'll adopt that way. I don't want to say you have to. It's for me, secondary method. Yeah. Yeah, it's all about just reducing that risk. Yep. Yeah, Jason is very much on point. Mixing it with boiler. Failure of bearings due to low oil pressure. Is there any chance of bearing failure due to... Yes. The chiller's not going to let you run Kahalid. The chiller's not going to let you run with low oil pressure for that very reason. It's got to protect the bearings, especially that journal bearing on the front side of the motor. If that doesn't have enough pressure, it can't pressurize the sleeve and lift the shaft off of the aluminum sleeve, which as soon as that motor begins to rotate, that steel shaft is going to shred that aluminum bearing. So absolutely, if we do not maintain proper oil pressure, you will destroy bearings. Yeah, starting. From experience, what has been the most difficult centrifugal chiller to do a teardown on? Most difficult. Daniel, I would say the most difficult would probably be York's centrifugals. And that's, on some level, it's all big, heavy lifting. Okay. But York, with their rotor assembly and how intricate and how precise each of those little things have to be, I mean, spot freaking on, if you want things to go smoothly. So, like for me, I feel a Trane centrifugal, specifically their direct drive, CVH style machines. Those are some of the easier ones. Doing a turbo core, because you can service turbo cores like that. Those aren't too bad to break them apart, service them. Um, I haven't done a YMC squared and the YZs, but looking at how they're configured, the compressor, those are pretty intricate themselves, but they're not as complicated as their gear drive, right? And let me let me show this. Let's go on a field trip. Come over here. Let me show you this rotor housing assembly. So come on. You can do it. Oops. Did that wrong. Let's try that again. So like right in here, this is just a small example of it, but in this whole housing, you've got the reservoir up here, you've got to get these gears set right. Your impeller goes up here. This is the end of your high-speed shaft. You've got a bearing here, bearing here. You've got another set of bearings on the backside there. Your thrust, your low-speed thrust goes here. You've got a high-speed thrust on the backside. All of these have extremely tight tolerances. There's just so much, and then you've got to get this whole rotor housing in the first place in a spot where you can even work on it and service it. And so, like, a lot of us have to build these yoke style turntables that we can mount this to, and I mean, it makes it easier, but again, it's a whole lot of extra work and complexity and effort that goes into being able to do that overhaul in the first place. So um yeah, that would be my opinion on, say, the hardest, and they're the most technical. I mean, don't get me wrong, every one of them have a lot of technicalities. uh your carriers aren't that, I mean, they're not that much different. Or let me rephrase, the 19XR style are not that much different than a white or York style high speed um, gear drive compressor. They're all like, how about this? Gear drive as a whole tend to be just a pain in the butt. Versus, in my experience, most of your direct drive compressors tend to be not that bad. I think that's how I'll distinguish a category. Gear drive, pain. Direct drive, not that bad. There. That's my answer. All right. I'm only asking because at first I didn't agree. But then I started doing it for safety, but kind of reluctantly. you know, this so Sterling, you're actually showing an exact point that um I've been trying to make for some time. And that is, there's a lot of unspokens Like, this is the exact conversation of the unspokens. We have processes and procedures that aren't always laid out. And we know these things because of the experiences we've had to go through to develop that knowledge. It's not like there's a lot of stuff that we didn't learn from somebody else. We didn't learn from a manual or a book or anything like that. We learned it that way because we've had to live through the downsides of it so many times. But then, as an experienced tech, being able to communicate all of those things we've had to learn to someone who hasn't, it's one, it's just not even something that most even think about or consider. It's just not even a thought process. And then two, it's difficult to really summarize those because as you gain experience, there are certain things that you start to think to yourself, this should be just kind of baseline, basic common knowledge. I shouldn't have to break this down for you. But in reality that's not true. Um, that's just not true. But it's hard to have that perspective, and it's hard to keep that in mind. So, yeah, to your point, you're reluctantly doing it because you're told you say should, but you don't really understand necessarily the why. And that's because there's a whole sequence of unspoken experiences that you haven't had to have that somebody else may have, and it's become their why and their understanding of it. And sometimes those can be wrong. Like I'm definitely an example of that. There's quite a few things that I learned the wrong thing through experience. And it took being corrected or going through other experiences to then correct what I learned wrongly the first time. I'll give a prime example of this. I was weak on pressure enthalpy concept and as a theory. And so I um, I thought that flash tank economizers specifically were creating additional subcooling the same way that a plated or a braze plate economizer does. I thought these things were fairly similar in the way that they were functioning, just did it in a different form. One were flashing the refrigerant off. Reality is that was a bad concept. I wasn't understanding the pressure enthalpy relationship appropriately, and that led me to thinking of it in the wrong way. So I've had to correct that, and I've had to go back and do a lot to correct that because I taught that the wrong way for quite some time, and I taught that flash tank economizers did produce additional subcooling, and that's not true. They reduce enthalpy, which helps increase effectiveness, but it's not subcooling. There's a difference. So, yeah, sometimes we have to relearn things because we didn't quite get it right the first time. Anyway, should Sabbath keepers be on call in our industry on Sabbath? This is a great question. Let's talk about it. So, if you're not comfortable with a, call it religious, if you want, topic, then I would just ask that you just give me a moment to kind of speak on this and share. So, Sabbath, if you don't know, is a day where we take completely off of work. So part of Sabbath is you do not you do not engage in work. Now, depending on exactly what you believe, will vary a little bit on what kind of Sabbath you keep. So at minimum, you shouldn't exchange money. Like, you shouldn't pay for things, which is making somebody else work. That is something that a lot of Sabbath keepers believe. I being one of them. We do not eat out. We don't go to the store. We don't go get things on Sabbath. On some, like, one example of where I will differ on Sabbath from others is I will go out and tend to my chickens and tend to my sheep on Sabbath. And when I say tend to them, I mean feed them and make sure they've got water and take care of them. But there are some who believe more strictly than that, and that's your choice. To not work, like not even do that much. And part of that is the day before you should do enough to prepare so that you don't have to do it on the Sabbath. And the whole concept is to take a day of rest and break and have a time of connecting with our Yahweh, our God, our Jesus being Yeshua. So to give a real quick highlight on my stance personally on this topic. So I am a Christian, but I believe in Christ and in His redemption. But I do follow what we refer to as Torah, and me and my family have taken time to study Hebrew and Jewish practices in this way so that we better understand it. I do follow this, not because I don't see it as a salvation issue. Now, you that asked the question, sorry, your name, James. James, you may see this differently than I do. So this may affect how you view my answer. And I do want to clarify where my answer is coming from so that you fully understand my position on this, because I do find that in the Sabbath community, there are a lot of perspectives people come from and why they believe what they do. So it is my opinion that the Torah and the law, because of Christ, is not mandated the way that it was prior to Christ. And it is not tied to your salvation. Christ gave forgiveness and salvation. Now, me and my family choose to follow Torah because it is a set of instructions on how Yahweh would like us to conduct ourselves and to live our life. And now, it is not possible to follow these perfectly. The scriptures repeat that often. The whole point is we are fallen in our sin, so we cannot perfectly adhere to the law and Torah, which is a huge reason why Christ was even necessary to begin with. So, depending on, again, what you follow, I follow call it a Hebrew Sabbath, where Friday, so it's sundown to sundown. The Hebrew day is built on sundown to sundown, and there's a whole lunar cycle that goes into it, and it's very different than the call it a Greek calendar, which is what most of the West goes off of today. It's a Greek sun up to sun up, or actually not even sun up in some cases. It's 12 a.m. to 12 a.m. type of schedule and calendar, and the days are split that way. And those are very Greek mentalities. And I didn't grow up this way, by the way. This is something I came to with my wife far later in life. I grew up as non-denominational Christian. She grew up Baptist. So, anyway, so I do a Friday to Friday. I'm sorry, Friday sundown to Saturday sundown. That is my 7th-day Sabbath. That is what me and my family keep. Now, scale that to being a technician. It is really difficult. And this created a major struggle because I want to serve Yahweh the way that He explained to me he would like to be served. That is my goal. I want to serve him the way he said. I see the Torah as a way of doing that. But I did two things. One, somewhere along the way, I realized that I live in a world that does not believe what I do, that does not see things the way that I do. And I had two options. I could either make sacrifices to work at a company that they would work with me on that, or I could choose better prosperity. And that meant having to, on my own call, sacrifice my Sabbath. And that is the path I chose. I'm not saying it was the right path. I did eventually work myself into a management role where I could get off of the on-call schedule. And I didn't have to do that anymore. There were some major projects where I did, but we're talking maybe twice a year, something was going on that I ended up having to sacrifice my Sabbath for it. And beyond that, I was able to build a life and a schedule that fit around my Sabbath. And yeah, I don't know that I fully agree with my approach, because it is hard in the spirit of I want to serve him as best I can, as closely as I can. At the same time, I do accept the fact that Christ paid the price to give me that freedom to choose. And I don't use that lightly. I don't use that sparingly. And that was one situation that I chose to kind of draw a middle ground. So I'm not saying that I am an example of what you should do. I am saying that we're in a very difficult position because most of the rest of the Western world does not agree with us and does not understand our way of life and why we choose it. And we just have to make the best of it that we can in the circumstances that we are. I could condemn myself and say that I was more interested in providing financial security than I was serving my God with making the choice that I did. And it's a very fair position for me to take against myself, because that is the choice I made. I could have figured something else out that didn't mean sacrificing my Sabbath, but it meant my family sacrificing financially. I chose my path at the time. You have to choose yours. This was mine. Okay. Thank you for the question, by the way. These are things I very much believe. What I'm doing is a calling, and it is a ministry for me. I want you to be helped and benefit from the road I've had to walk so that I could try to make yours better. That is my goal. And I don't see it as my responsibility to use this as a platform to evangelize, so I don't do that. And there's a fly buzzing around here. If he makes his way into the scene occasionally, I'll deal with him later. So yeah, that's why you don't hear me talk about this stuff much or often or anything like that, because I just don't see that as my place. But I'm very happy to discuss these things with a question. All right, thanks. But my question is, if there is a bearing failure, will it be because low oil pressure? Some of Trane technicians told me that probability of bearing failure is high in CVH chiller with 514 gas. So the Trane techs may be aware of some kind of oil, and I don't know if 514 made them change oils potentially. So that's possible. Again, especially if this is a retrofit. So Khalid, it may be that you have a retrofit system and there may be some tolerances difference, right? So maybe the bearings that were probably 123, I would assume. So that everything was designed for that. What was it? It's POE, Trane 22 oil. Pretty sure it was 22 that they use on those 123 CVHs, which is I'm pretty confident it's a POE oil. Yeah, so maybe there's a different oil being implemented with 514. I don't actually know this from memory. I'd have to look it up and verify this. But that being true, the bearing tolerances may need to be a little bit different. And so I would imagine that the new machines that come 514 from the factory probably have this taken into account. And that while doing a retrofit will technically work, like these Trane techs are saying, they're seeing that it's causing a lot of bearing failures, having or doing the conversion because of the tolerance requirements and how they changed from one oil to the other. Because the oil, I think, has far more to do with that equation than anything else. So, will it be because low pressure? Some told me that a bearing failure is not guaranteed a low oil pressure problem, but low oil pressure is extremely likely to be the culprit of a bearing failure, or your oil having an issue in general is extremely likely. They're very, very, very much correlated, especially with those style of bearings that are a sleeve. So let's talk about that real fast. In case you're not familiar with the style, let me pull this up. I've got a quick example I can show you. So right here, this is the style of journal bearing that's in there. Now, when I say journal, the journal is the actual motor shaft itself, okay, the compressor shaft. So that is the physical journal. So when you see crankshaft journal, that's what's being referenced here. And then we have this aluminum sleeve that sits inside the larger compressor body. So the steel backing you'll see referenced, that is the actual compressor housing. Then you have this aluminum sleeve that can be replaced, and that's what we're doing. Now, this little line right here, and it is just a very tight tolerance. This is where we're going to have an oil film injected into in between the shaft and the bearing housing, so that we can literally lift and, for all intents and purposes, levitate that shaft, so that that shaft is not actually making contact with this aluminum housing. Now, if there's something wrong with our oil, if it is deteriorating, becoming it's doesn't have its lubricating properties it needs to, which will happen with age when they start to get real dark and nasty looking, that is evidence that that oil is beginning to degrade. Even if it may test fine in terms of it's not acidic, it's not latent in moisture, but it still has that dark discoloration to it. Well, that oil is beginning to age. It needs to be replaced. Otherwise, this tiny little film that we need, and this is what the pressure differential is doing, is we're pressurizing this region right here so that we can create a separation, because the oil is the actual rotating surface. With ball bearings, we have an inner race that stays mounted to the shaft, and um, the balls are allowing, that is our rotating surface, if you will. Where with a sleeve journal like this, I think I've heard this referred to as a Babbitt style, or Babbitt. I think it's Babbitt. Anyway, with this style, we're actually rotating on a oil film. And if we cannot pressurize this sleeve properly and maintain this film in here, then this shaft will make contact with this aluminum housing, and it will shred and destroy it. So if by changing the oil, that oil has slightly different properties, and maybe it requires a slightly different gap in here, or the tolerance is changed, then you could be having more the failure rates could be increasing because of that specifically. And it either way, the oil on these types of bearings, which that is your front bearing, that's your inner bearing. Your outer bearing on that CVH is going to be a set of ball bearings. That's your thrust. So that's where your axial thrust, because those sleeve journal style bearings don't have, they can't control axial load. They can only control your radial loads, which is your up and down, side to side. That's not your in and out. So your axial load is your in and out load. So the ball bearings are really good at taking axial thrust loads. So they refer to those as your thrust bearings, because they're able to help mitigate thrust events, which surge being a prime example of extreme thrust being put against your motor bearings or your compressor bearings. And so those operate like a standard ball bearing. They're oiled. We're still injecting oil into them to keep them lubricated. But the main one that's going to fail the fastest, in my opinion, will end up being that journal bearing on the inner side of your compressor motor. What if learning is making mistakes? Yeah. Oh, I see your other comment now there. Khalid is, yeah, they're saying the journal exactly. Yeah, the journal bearing is what I would expect to be that, and then you've heard my breakdown as to why I would have that opinion. My YK chiller seems to be running with high refrigerant charge. How can I confirm if it is overcharged? And we got a few more minutes, so I'll try to wrap up as many questions as I can. Feel free to still get them in. I will go back and save all the ones I haven't gotten to. Okay, so just because I don't get to yours does not mean I cannot get to it at all. All right. My YK chiller seems to be running with high refrigerant charge. How can I confirm if it is overcharged? So the simplest way I would suggest is utilizing your sight glasses. This doesn't have to be at full charge. This is still effective even at a partial, not full charge, I'm sorry, at full load. This is still effective even at a partial load. But with the machine stable, and here's the big thing, it's really critical. You have to have stable. You're at set points. Everything is stable. You're not having major fluctuations. You're not staging the PRVs. The metering valve isn't having to pivot nothing is being erratic. Everything is running stably. If you can achieve a very stable operation, then a correct charge should look like about 1/3 to 1/2 sight glass in the evaporator, and about 1/3 to 1/2 sight glass in the condenser. And the way that York, this isn't a perfect exact science. Most people think it is. It's really not, which is why we have to do filled trims sometimes. They calculate it at the factory if it should be about this, but then we have to then at commissioning determine, is that actually correct, or are we a little over, a little under, and then we can trim accordingly at the point of commissioning. So that still falls on our shoulders to confirm that as the qualified technician. But once you get those sight glasses about there, that's about where it should be. So one of the things you'll find is, well, that gets far more complicated than that. I don't know if I want to approach it that way. If somebody wasn't playing with it and changing things, one of the things I find is that when I'm starting to have a undercharge scenario, the condenser water, or the condenser refrigerant level, because that's what the YK is monitoring, the refrigerant level in the condenser, will be maintaining. And you'll start to see lower refrigerant levels in the evaporator because of it. So you'll still maintain your condenser level, but your evaporator level will be really low. Now, I have seen it to where when the machine is improperly charged or is struggling, maybe it's lost some charge, people will lower the condenser level set point, which will then increase our levels back in the evaporator, and that will work for a time. It will be less efficient, and you may get some subcooler seal loss alarms because of that, but that maybe some. So if you see that and you see you've got a really low liquid level set point, that'd be something to look to. Now, in terms of overcharge, if you're seeing substantially above half glass on either or both, say one is, what'll probably be more likely is if somebody overcharged it. Let's assume the condenser is correct and the liquid level set point and everything is correct on the condenser side. What you will very likely see is the evaporator side will be really high. And I've seen this before where it's spot on the condenser side, but it's over the sight glass in the evaporator. That is an overcharge. What you'll also see is that's going to have a heavy impact on your discharge superheat, which, depending on if you have a constant speed or variable speed, will vary what that discharge superheat will be in a given moment. But that's what I'll see with a YK is you tune everything to the condenser level. The condenser level is, in my opinion, the main thing you're trying to control. That's what that whole control panel and algorithm and everything is built around, is maintain this refrigerant level in the condenser. And it's about maintaining efficiency and processing through the subcooling rack. That is its whole thing. And then the evaporator, if everything is correct, charge is right, yada yada, then the evaporator level will be correct as a result, and that, like, everything will balance out. So I would tune that first. I would get that where it's supposed to be on the condenser side, and then I would see what my evaporator side is doing and where I'm at there. And that could lead you down many roads. Maybe it's not an overcharge. Maybe it's a liquid level set point problem. Maybe it's a liquid level sensor problem. Maybe it's a metering valve problem. So these components will affect where that charge sits, and depending on what your conditions are you dealing with high head pressure and high condenser approach? That could be the refrigerant level being set really high, as an example. But that also means that you should see lower. Like if the condenser is high, if everything's charged correctly, if you've got a high condenser level, that means you should have a lower evaporator level. Those things should balance out in that way. There again, if your levels are set too low, maybe you're dealing with a low discharge superheat problem, and that becomes your main issue. Well, then you're troubleshooting the liquid level set point being on the low end, or possibly the sensor just being bad, or the metering valve having an issue, things along those lines. So that would be the path I would chase if I was concerned about a charge issue, whether low or high, with a YK centrifugal. That's the process. Learn, fail, analyze, retry. Yes, very well summarized. RTHC, chiller, low pressure alarm, reset. Okay, I am out of time. Let's see. Okay. Verify all transducers and sensors. It's a Trane. Be nice. Be nice. Okay, I gotta go, guys. I really appreciate it. Really enjoyed today. Had a great time. Um, be sure, if you're interested, if you like getting involved in the stream here, go to the portal in the academy, chilleracademy.com. Go to the live or the chiller questions answered portal and get signed up in that, so you can get your questions in, get priority, see all the stuff, see what's coming up on the schedule. There's a whole system in there just to manage this side of things. Really appreciate everybody's time, and yeah, I will see y'all in the future. And if you're not in the academy, I've got a free course for you, by the way. If you didn't know that, go to chilleracademy.com, sign up for the free service course. We've got a lot I'd like to share with you in there, and then we can work together from there to get where you're trying to be in your career. Really appreciate it.